Good afternoon, everyone. This is Paige Graff, and I'm here with Liz Rampe. Welcome to the Curiosity Rover on Mars. Exciting discoveries continue. We are officially beginning today. We are broadcasting to you from the NASA Johnson Space Center in Houston. Now, a couple of additional opening remarks. First of all, welcome to all the participants on the line. We have 31 states participating in either the live and/or archive recording of this session. You can see the stars on the map. We've got some gaps we want to get some schools and participants from, but really we've got a great showing from the East Coast, from the South, from the North, from the West, and even here in Texas. Now, there are students on the line in grades K through 12, but we are targeting sort of a middle school audience because that's how the event was advertised. But we welcome all of you, including our group from Mexico, who is joining us as well. Now, for our featured speaker today, we are really, really lucky to be able to have Liz Rampe with us. She is extremely busy. She's going to tell you a little bit about herself in a few moments. But she's going to mainly be focusing on the Curiosity rover on Mars. So if you want to look up more information about the rovers, we have some websites listed here that you can certainly look at. But I think Liz is going to really give you some great information about the rovers on Mars. So again, welcome everyone. And I'm going to see if I can turn things over to Liz. Now, before Liz does start, Liz really is a very busy scientist. She's got a lot on her plate, but she is, and we are so lucky to have Liz with us today. She's fantastic. She's so excited about the work that she does, and I'm so glad that we have her here with us today. So Liz, with that, I'm going to turn things over to you to introduce yourself and share.
Great. Yeah, thanks, Paige. Yeah, so my name is Liz Rampe. I'm very excited to talk to you today. I'm a member of the science team on the Mars Science Laboratory Curiosity rover. I've been a science team member for, 6 years now. I'm also the deputy principal investigator of one of the instruments on Curiosity. It's called ChemMin. It tells us about the minerals that we find in the rocks and the soils in Gale Crater, and I'll tell you much more about ChemMin in a little bit. My background is in geology. I grew up in Denver, Colorado, so of course loved the outdoors. My parents took us, my sister and me, hiking and camping, and so that's how I fell in love with the natural world. From there I went to undergraduate school at Colgate University in upstate New York and studied geology there, and from there went to Arizona State University in Tempe, Arizona, and got my PhD. I graduated in 2011 with my PhD, then came here to the NASA Johnson Space Center in 2011 to do my postdoc, and was eventually hired on, and now I'm a civil servant. So that's a little bit about me, and so I am a planetary geologist. Let me see if I can turn those down. Okay, so yeah, I'm a planetary geologist. I study Mars. I'm especially interested in the minerals that form from water-rock interactions. Those types of minerals can tell us what water was like on Mars a very long time ago. And so let's keep going. So I'm a planetary geologist, but let's start by talking about what geology is. Geology is the study of the Earth's physical structure and substance. So what it's made out of, the chemistry, the minerals, both on the surface and in the interior, its history, but also the processes that act on the surface. So things like volcanism, volcanoes, plate tectonics, earthquakes, plates, geological plates moving, but also wind and water depositing and distributing sediment across the surface. And this is a picture of me, for scale, in Iceland, doing some geology. This is a volcanic neck. So this occurred where some lava was about to erupt but didn't quite erupt on the surface, and so it formed these beautiful columnar joints is what we call them. So I'm a planetary geologist, so I do geology on the Martian surface. And so I have a question for all of you. How do you think scientists do geology on other planets? What sort of tools can we use to learn about the geology of other planets? So please put your answers in the chat window.
And so this may be a tough question, but we want to get some of your thoughts. So Duxbury Senior Center jumped right in and said through photography. MacArthur is saying, or Corpus Christi is saying robots. Shaker Heights in Ohio says remotely using rovers. Smith Elementary in Delaware says satellites. Nebraska City Middle School also mentioned using robotics. Green Park Lutheran says send a rover, scan the rocks. Smith Elementary added in photography. Monmouth Middle School says to take samples with rovers. Meadow Creek talks about rovers and scanning. Nebraska City Middle School also mentions lander or landers on the surface. NMMSH mentions spectroscopy. Texas Space Grant also adds in remotely using satellites or rovers. Space probes from Harrison Intermediate. Observations and rovers from Murfreesboro Middle School. Leon Springs says geologists study and examine photos and soil samples from rovers. Palm Springs North indicates that they can investigate areas on Mars. I'm hearing rovers and space photos and landers and spectroscopy. We've got a lot of good answers, but I think some of the other answers are going to surprise folks.
Yeah, so you guys have got most of them. So obviously we've got observations from telescopes, measurements from orbiters, some of which do spectroscopy, which I'll talk a little bit about today. So the New Mexico School, great job. We do measurements from landers and rovers. A lot of you got that too. One thing we can do also is to return samples from another planet. We have not yet returned samples from Mars. That's hopefully in the next decade or so. But we have returned samples from the moon. We can also look at meteorites that come from these other planetary bodies. And so that happens when a large impactor hits the surface, sends rocks shooting out every which way. And sometimes Earth is just so lucky that we are in the path of some of those rocks that were ejected from another planetary surface. So we can collect them and study them in our laboratories. The other thing we can do is we can send people. So, of course, we have not yet sent people to Mars, but we have sent people to the moon in the Apollo era, and hopefully coming up in the next decade or so. So, yeah, great answers. So Mars has, or NASA has sent over a dozen missions to Mars. They really started in 1960 with a few flybys, so where a spacecraft just flies by the surface of Mars and takes pictures. And the results from those initial flybys were kind of disappointing to people. Before this, some people thought that Mars might have had active rivers and lakes. Some people even thought there could have been a civilization on Mars and building canals. So you can imagine the disappointment when they flew by and saw, you know, a sort of desolate cratered surface that was not unlike the moon. But later on in the 70s, with the Mariner 9 orbiter, they collected a lot of images that suggested that Mars was much more Earth-like in its distant past. So this image from Mariner 9 shows a volcanic crater, so suggesting that there were volcanoes or active volcanoes at some point in Mars's distant past. Then in the late 1970s, there were the Viking missions, which were a pair of orbiters and landers. Those were the first landers to go to Mars. In 1997, there was a fantastic mission, Mars Global Surveyor, that took global photography of the surface and suggested that there are a lot of sedimentary rocks on the Martian surface. 1997 was the first rover that was a pathfinder or sojourner. 2001, an orbiter was launched that we still use today to send commands to Curiosity and to send data back to Earth. And Mars Odyssey had a really great spectrometer on it that could tell us about the minerals on the Martian surface. 2003, this isn't a NASA mission, but Mars Express was a really important mission for, it also carried a visible near-infrared spectrometer that could tell us about the minerals that form from water-rock interactions on the surface of Mars. In 2004, the Mars exploration rover Spirit and Opportunity landed. Spirit, I guess, died in 2008, but Opportunity is still going, I guess, almost 14 years later, which is pretty amazing. 2006, there was another orbiter that we also still use to relay commands to and from Curiosity. 2008, there was a lander near the North Pole, and finally in 2012, August 2012, the Mars Science Laboratory Curiosity rover landed in Gale Crater. And this is just a little rover family portrait, so you can see how big these rovers are. So this is Pathfinder or Sojourner that landed in 1997. It's about the size of a microwave. This is the Mars Exploration Rover Spirit and Opportunity, so about the size of a golf cart. And here is Curiosity, and she is about the size of a small SUV. So very large, can do a lot of science with her. So now the next question is, why do we scientists care about exploring Mars? Well, we know that Mars has geologic features similar to Earth. We saw some of those earlier with those volcanic craters. We also know, based on these geologic features, that water once flowed on Mars. And so we want to know if Mars could have once supported microbial life, because life as we know it on Earth requires liquid water. So now I have another question for you all. What evidence supports liquid water once being on Mars? Is it A, we see water on the surface today, B, surface features provide evidence of water that once flowed across the surface, or C, remote sensing instruments detect minerals on the surface that form in water? So please put your answers in the chat window.
So we're getting some quick answers in right away. NMMSH says C. Shaker Heights says C. Leon Springs says B and C. Corpus Christi Catholic School says C. Jenks High School says B. Central Heights says all three. Smith Elementary is mentioning B and C. Duxbury thinks it's all three. Harrison Intermediate thinks maybe C and B. Meadow Creek, just C. Green Park Lutheran, B. York Middle School, B. B is a very popular answer. I think you might have mentioned something about that. Nebraska City Middle School says B and C. Murfreesboro Middle School in Illinois says B and C, as does Monmouth Middle School and Meadow Creek. So we have a lot of B's and C's.
Lots of B's and C's.
You, all three. So I'm really curious, Liz. These are great answers.
Great answers. And so B and C certainly, possibly A. So we do see these dark slope streaks on the Martian surface today that could be from liquid water. But we certainly see ancient river and lake deposits, and we detect minerals that form from water-rock interactions like clay minerals and salts. So let's break this down a little bit. This is supposed to be a video, but it's not right now.
Yeah. Will the next one show
the next one? Okay. So no worries. Okay. In the spring and summertime in craters, impact craters near the equator, there are these dark slope streaks that form. And there are a couple of hypotheses as to how these form or why they form. One is that they are related to liquid water, where these surfaces actually have salts that are hygroscopic. And hygroscopic means that they can suck up water from the air, so much so that they actually liquefy and become, a solution and flow downhill. But a recent paper that came out maybe a couple of weeks ago suggests that these dark slope streaks are not from liquid water, that these are just dry granular flows. Water might be involved where, since they form in the warmest time of the year, so maybe there's some sort of frost or some other water that holds these grains together and eventually melts so that these granular flows can form. But, scientists are still puzzling about this, so don't put your answer in the chat window, but just think about, what makes sense to you. Do you think these form from liquid water or not? Okay, but let's move on to the geomorphologic evidence for liquid water on the Martian surface. So this is an image from Earth. This is a fan or delta in Mongolia in Lake Baikal. And this is where a river flows into a lake and sediments are deposited. You can see this nice crescent-shaped or fan feature. And here is a fan that we found on Mars. Again, you can see a very beautiful crescent shape, and this is evidence for water having flowed into a crater about 3.5 billion years ago on Mars. So, and this is another image from Earth. This is a system of river channels in Yemen. And you can see a similar system of river channels in these deposits on Mars. Again, these are about 3 billion years old, so suggesting there were rivers there. Another line of evidence is through the minerals that we find on the Martian surface. This is a color image from an area called Marth Vallis. It's actually a massive river channel. But if we could see in the infrared, so in wavelengths that are slightly longer than what our eyes can see, we would see that there are hydrated minerals or minerals that have water in their structure, suggesting that they formed or telling us that they formed from water. So these different colors show you where some of these minerals are. In reds and greens are what are called clay minerals, and they're hydrated silicate minerals, but they require a lot of liquid water to form. And in blue are sulfate salts. So those form in, obviously, less water and saltier water, sometimes more acidic waters. So now, let's see, this is, okay. You're probably wondering what happened to all of Mars' water. Well, this is just a little video to show you what we think happened. So I'm going to take you back to Mars about 4 billion years ago. And Mars might have looked pretty Earth-like. You would have seen rivers and lakes. There would have been clouds. It might have rained. It probably snowed. But this looks like a pretty nice place for a vacation. Like, have a seat. Anyway, about 3.5 billion years ago, Mars lost its magnetic field. And the magnetic field is what protects its atmosphere and the water on the surface from loss to space. And so once Mars lost its magnetic field, there are high energy particles that can come down and strip its atmosphere so that water on the surface was lost to space. And so that's what around 3.5 billion years ago is when Mars started to become this more desert environment that we know it as today.
Sure. So that's a pretty neat video.
Yeah, I love that video. It's so good. Thanks, Paige.
Sure.
Okay, so that brings us to Curiosity and why we landed at Gale Crater. But this is just a map of Mars showing you where we've landed previously. You can see Spirit and Opportunity, we're near the equator, Pathfinder, the first rover here, Viking 1 and 2 across the planet, and then Phoenix near the North Pole. But Curiosity landed in Gale Crater around the equator. And Gale Crater is an impact basin that's about 90 miles across. And what's really interesting about Gale Crater is that in the center there's this mound of layered sedimentary rock in the middle called Mount Sharp. It's about 3 miles tall, and the layers in the bottom we know from spectroscopy and remote sensing. We know that they contain minerals that suggest they were deposited in liquid water, and they suggest that these waters and climates changed over time. And so if we could, again, see in the infrared, we would see, so this is just zooming into those lower layers of Mount Sharp, we would see that the lowest layers have a lot of clay minerals. Again, those minerals require a lot of liquid water to form, and they form around near neutral pHs. And then in rocks that are above the clay minerals, so rocks that are slightly younger, we see many more sulfate salts. Suggesting that those sediments were deposited in saltier waters, and maybe the water was less abundant. So the idea for Curiosity was to land at the base of Gale Crater, studying the oldest rocks, and then to drive upslope to younger and younger rocks to see how these environments and climates changed over time by looking at the geology, geochemistry, and mineralogy. So Curiosity's primary scientific goal is to explore a local region on Mars' surface as a potential habitat for life, past or present. So we have instruments that can assess the biological potential of these environments, to measure the geology and geochemistry, to look for radiation hazards, and this is especially important for when humans go to Mars because we need to know about the radiation environment to prepare for habitats and spacesuits. And finally, we have instruments that can look for water, generally in minerals, not liquid water on the surface, but also look at the weather on Mars. And speaking of the weather on Mars, I have a question for you all again. What was the high temperature at Gale Crater yesterday? I will tell you, it is winter there. But was it 50 degrees Fahrenheit, which is about what it is outside here? Was it 32 degrees Fahrenheit, so was it freezing? Was it 0 degrees Fahrenheit, or was it minus 30 degrees Fahrenheit? So what was the high temperature yesterday?
So York, Green Park, Lutheran, and Meadow Creek, they all think minus 30 degrees. Smith Elementary is toggling between C and D. Harrison thinks minus 30. Shaker Heights thinks probably minus 30 as well. Central Heights is thinking possibly C. Pine Lane, D. Palm Springs North, D. And these temperatures I hope none of us ever feel. Alpine Middle School says C. Corpus Christi Catholic School in Pennsylvania says D. NMMSH says C. Monmouth, Nebraska City Middle School, Murfreesboro, Peavine, they all think D, minus 30. Ford Elementary thinks possibly C, that it's about 0 degrees.
Gosh.
So they're all kind of cold in my opinion, but yes. What was the high? I can only imagine the low.
Yeah, the high temperature yesterday at Gale Crater was minus 30. So you all were very right. It's very cold there. But the low yesterday was minus 80. So
minus 80 degrees Fahrenheit. So that's pretty cold.
Yeah. In the summertime, we can get up to maybe like 40 degrees Fahrenheit. So, well, maybe like close to what it is outside.
Okay. Good answers. And I don't want to live on Mars, at least not forever.
All right. So you guys got it. Okay. So let's talk a little bit about the instruments that Curiosity has. I'll start at the top. ChemCam does laser-induced breakdown spectroscopy, which means that it shoots a laser up to maybe 15 feet away, that can ablate part of a rock or soil, and it turns that into sort of a plasma, and it uses a spectrometer to look at the elements that are present in those rocks and soils. Below ChemCam, we have NASCAM, and those cameras give us those gorgeous outcrop to horizon view images that I'll show you. Our weather station, REMS, is on the neck of the rover. We have an instrument to look for subsurface hydrogen, which we think is present generally as water in minerals. We have our radiation detector. Out on the arm, we have MOLLE, which is a hand lens imager, so it can give us close-up views of rocks down to a resolution of about 60 microns per pixel. We have APXS, which gives us bulk chemistry. We also have our sample handling system, which includes the drill, the scoop, the brush, and the sieves. When we look on the inside of the rover, we have SAM, which heats up samples to about 800 degrees Celsius and looks at the gases that are evolved from them and can identify organic molecules or the building blocks of life. And finally, we have the instrument team that I'm on, ChemMin. It's an X-ray diffractometer, and it tells us about the minerals that are present in the rocks and the soils. And you all know how important the mineralogy is for identifying environments that once had water. Okay, so this is our traverse from our landing site up at Bradbury Landing, is what we called it, down to the layers of Lower Mount Sharp. And we entered those layers of Lower Mount Sharp down at Rump Hills. And this traverse is a little over 11 miles, so we've gone a little over 11 miles in about 5.5 years. And this inset here shows you where we are today. Yeah, this was about 4 days ago. So I think we're still there, up on this ridge called Bureau Ridge. So what I'm going to do is I'm going to walk you through some of the locations that we've been along our traverse, show you the rocks, and talk about what they're telling us about what Mars was like, or what Gale Crater was like 3.5 billion years ago. So we'll start with the landing site. This was the first image that was returned after our landing, and actually we had a very spectacular and unique landing. All rovers previously and landers landed on the surface with airbags, but Curiosity was so heavy that would not work. So we used what's called a sky crane, and it's a separate vehicle that has retro rockets that just gently place Curiosity on the surface, suspending her from cables. Those cables were cut, and then that vehicle went and crashed somewhere else. Okay. But from those retro rockets, we scoured a lot of the surface surrounding the rover, and we made some really spectacular discoveries. We found this rock nearby. It's a conglomerate, and if you take a closer look, a conglomerate is a sedimentary rock, which is made up of a bunch of different sized particles. And the rounded pebbles and sand in this conglomerate rock indicate that water once flowed here in a river that was about ankle to hip deep. So pretty incredible. I have another question for you. So this is a high-rise orbital image of a Gale crater. This is Mount Sharp down here. These are those lower layers of Mount Sharp. Can you identify an area where an ancient stream bed may have deposited material in this image? So look for an alluvial fan. Remember those fan, like crescent shapes. See if you can find it. Is it in quadrant 1, 2, 3, or 4? Can you see it?
So if you can see it, describe where in the particular quadrant so we know where you might be talking about. Because York Middle School and Leon Springs are mentioning quadrant 4. Central Heights is thinking 2, but give us, so here's Ford Elementary says bottom left quadrant 1.
Bottom left quadrant 1.
Duxbury's thinking maybe quadrant 4. Peavine is thinking both 3 and 4. Central Heights is thinking possibly northeast quadrant 2. Good description there, Central Heights. Smith Elementary and Monmouth are mentioning somewhere in quadrant 2. Palm Springs North says possibly 4. Duxbury has changed their mind. They like the bottom of quadrant 1 now. Green Park Lutheran, number 2, quadrant 2 in the upper right. Nebraska City Middle School is thinking possibly bottom right of quadrant 2. Murfreesboro says possibly 4. Meadow Creek Northwest quadrant 4. Corpus Christi Catholic School thinks 2, 3, and 4 all have an area where it looks like there could have been an ancient stream bed. Jenks High School says 2 near the center flowing from the top. York Middle School mentions the bottom quadrant of 2. And NMMSH says all seem to have features that could be associated with water. Meadow Creek is saying 2 and 3. So I like how we had some northeast of this, northwest of that, bottom quarter of quadrant 2. This is tough because there are a lot of things that really look like potential water areas.
Yeah, and I liked the NMMSH's answer that there are a lot of features that look like they could be river channels, and it's true. There's probably river channels in all of these quadrants. And
Leon Springs did revise their answer, and revisions are always good. Top left side, possibly, of quadrant 2.
Yeah, and I think Jenks High School described it the best. They said, flowing from the top to the center of quadrant 2, and that's exactly right. So if you look here, you can see this channel flowing down, and there's this fan feature here. It's really faint and hard to see, but some of you saw it. So great job. But there's actually, there's fan features around here, and I'll actually point out one later that we're going to visit down here. So good eyes, everybody. Okay. So this is a high-rise image, an orbital image showing Bradbury Landing, and then from Bradbury Landing we drove over to a place called Yellowknife Bay. We drove over here because there was a conjunction of 3 different rock units where you can see this brightly colored unit, there's this sort of light tan, and then there's this dark brown unit. And in this high-rise image, this little white dot here, you can actually see Curiosity doing her investigations of Yellowknife Bay. And this is just an image showing from Mastcam of driving down into Yellowknife Bay. This is the crater rim in the background. And there's a few different rock types at Yellowknife Bay. There's this buff fractured mudstone. Mudstone is a sedimentary rock that has very fine grains, grains that are so small that you cannot see them with your eye. But then there's a sort of gray colored sandstone up here. Those are coarser grains that you can see with your eye. We also saw some veins at Yellowknife Bay. This is an image taken by ChemCam showing these bright colored veins. Again, ChemCam can shoot that laser to identify the elements present. And when it fired its laser, it found that these veins are enriched in calcium and sulfur. So a lot of the veins that we see are enriched in calcium and sulfate, suggesting that waters were moving through here that were enriched in both of those elements and precipitating those salts. And this is just an example on the right side from Earth of similar veins. In the mudstone, we see these little spherules, which suggests that there was water percolating through pores in the wet sediments before they lithified. We also see these raised ridges, which are actually enriched in magnesium, also suggesting waters that were enriched in magnesium were flowing through or moving through these sediments before they were lithified. So we decided to drill here, and this is just an image showing the placement of the drill on the rock. And these are our first drill holes into Mars. For size, that's about the size of a dime. And we drill down maybe 5 or 6 centimeters, so only a few inches down. So they're pretty small. And so now I have another question for you all. How is the drilled sample from beneath the surface different from what we see on the surface? So how is this powder that's produced by the drill different from the surface out here?
So let's see what answers we have come in from the chat window. All of these observations are such an important part of science. So we'll see as they think about it. So Duxbury is mentioning it hasn't been oxidized, and we might come back to that to describe that a little bit more. We have Green Park Lutheran, the color is lighter gray. NMMSH is less oxidized iron. Leon Springs from Texas says the color and texture is different. Central Heights mentions it's not oxidized, it's a lower level of the surface. Monmouth Middle School says also less oxidized, lighter color. Alpine Middle School mentions at the top, the surface is brown/red and the subsurface is gray. Great description. Smith Elementary mentions to the point, different color. Ford Elementary, the color is lighter and more powdery. Murfreesboro mentions that it's gray and the surface is reddish. York Middle School says, and they're from Maine, the exposure to atmospheric gases are possibly different, hence you have a color change. Peavine from Nevada says it's gray, maybe because the iron has been sheltered. And Nebraska City Middle School says lack of red means less iron. The gray also looks finer. And Meadow Creek adds in texture and color different, may be associated with water. And what I love is they're giving reasons behind some of their answers, which is such an important part of science, wouldn't you say, Liz?
Oh, absolutely.
Excellent answers.
So, yeah, excellent answers. Not only did you identify that the drilled sample is gray and the surface is red, but you also came up with some very important hypotheses and very interesting hypotheses as to why the subsurface is gray and not red. And a lot of you brought up the point about oxidized iron. And yes, iron in its reduced form is not red. Iron in its oxidized form is red. So there is a mineral called magnetite, which has both oxidized and reduced iron, but it is a black mineral, which we find in this sample here. Whereas hematite has only the oxidized form of iron, and it is red, which causes a lot of the samples that we find elsewhere to be red. And we've actually drilled 16 samples so far. So this was our first sample that you just saw, but it shows you that all of these different drill tailings are different colors. And those different colors suggest that there are different minerals present. And a lot of that has to do with the presence or absence of oxidized iron and the presence and absence of the mineral hematite, which gives these drill finds their red color. So good job, everybody. Okay. So after we drill a sample, we deliver it to Kenman on the inside of the rover to tell us about the minerals that are present in those samples. And I just want to show you a quick video of how Kenman works. So we deliver the sample, and it goes into one of 27 different sample windows, which is in a wheel configuration. Then we transmit an X-ray beam through the sample, and of course you can't actually see X-rays, but just pretend like you have X-ray vision. So as an X-ray beam is transmitted through the sample, that sample is being constantly agitated by piezoelectric pulses, so we get all different grain orientations, and so that all the different grains can get into the beam. As those X-rays are transmitted through the sample, minerals have a distinct characteristic crystalline structure, and so these X-rays are diffracted off of atomic planes in those structures, creating characteristic X-ray diffraction patterns that we can use to not only identify which minerals are present, but we can say in what abundance they're present too. And this is the X-ray diffraction pattern from that John Klein, that gray drill powder that we saw previously. Many of these bright X-ray rings are from basaltic igneous minerals, but this halo down here is from phyllosilicates or clay minerals. And we actually found about 28% clay minerals in the sample, suggesting that there was once a lot of liquid water here. So based on our observations of at Yellowknife Bay, we know that life could have existed here based on the geology and that fine-grained rock telling us that there was a lake here. Again, the minerals tell us that there was water here that was not too alkaline or acidic. We found all the key chemical ingredients for life, like carbon, hydrogen, oxygen, phosphorus, nitrogen, and sulfur. And we know the presence of magnetite, not hematite, tells us that the conditions were not too oxidizing. So let's move down the road a little bit and let me show you a few more images of Gale Crater. So from Yellowknife Bay, we drove down to a place that we called Winjana, or the Kimberley. And here's a high-rise image showing you some of those rocks from orbit, and you can see Curiosity checking out what we call the striated unit, or this sort of lineated or stripy unit here. And from the ground, this is what that striated unit looks like. It's these sandstone beds that are dipping or tilted ever so slightly towards the center of the crater. And actually, this is exactly what a delta deposit or a fan deposit looks like from the ground. So we know that these sediments were deposited in a delta. From the Kimberley, we finally got to those rocks at the base of Mount Sharp when we arrived at the Pahrump Hills. And this is an image of the Pahrump Hills outcrop. This is our traverse that we took through Pahrump Hills. We actually did this 3 separate times. And this traverse is maybe a little over a football field in length. And these are the different stops that we took on the Pahrump Hills. We made some interesting discoveries here. One of them is, if you can see this brushed surface of the rock, there are these tiny millimeter scale rice grain-like toned crystals that we think are reminiscent of basically salt crystals that would have precipitated in these sediments. We found more mudstone, so similar to what we found at Yellowknife Bay here. So these are mudstones that have layers that are about on the order of centimeter scale, but we also found layers that are on the millimeter scale. And finding these laminated or layered mudstones suggests deposition in a lake environment. So we know that there were lakes at Pahrump Hills. From Pahrump Hills, we drove a little further down the road to Marias Pass. And at Marias Pass is where we saw a contact between 2 different geologic units. So this Murray mudstone is that mudstone that was deposited in a lake, and then overlying it is something we call the Stimson sandstone, which is actually a lithified or fossilized aeolian or wind-blown dune field. And from Marias Pass, speaking of dunes, we went and checked out some active dunes. So this is a high-rise image showing you some of those dunes that we looked at. This is High Dune and Namib Dune. We looked at both of them. So let's look at what they look like from the ground. Here we're looking at the Stoss slope of High Dune, and you can see some ripple marks on High Dune. And then this is the lee slope of Namib Dune. And for scale, this is maybe 12 feet high, so it's a pretty tall dune. And so the Stoss and the lee slope are formed when, so the Stoss side is where wind is blowing over it. It forms this long long slope, and the lee side is where these grains are coming over after they're blown off of the dune crest. And so if we were looking at the Stoss slope, so wind was moving this way, and then wind would have been moving this way. Further down the road, we found some really interesting evidence for ancient groundwater in Gale Crater. You can see these little sort of rounded materials, or they're what we call concretions. They form from waters moving through sediments before they are liquefied. We also see some interesting veins. So along these fractures, you can see that it's light toned, whereas the rest of the rock is red. This is gray, suggesting that there were waters moving through here that may have been reducing, not oxidizing. Again, so we also see some fossilized ripple marks. So you can see these swoop features in here. These sort of scoopy features are from after ripples migrating across the surface were liquefied. And finally, we found this very interesting outcrop, which we called Old Soaker. And if you look very closely, you can see these marks on the surface of the rock are actually ancient mud cracks. So this rock tells us that there was once, drying, desiccating waters in Gale Crater. So based on everything that we've seen about Gale Crater, we know that it once had a system of rivers, lakes, and deltas about 3.5 billion years ago. We know that groundwaters moved through these sediments, and actually we've dated some of the minerals in the sediments that suggest that those were deposited a little over 2 billion years ago. So that means that there was liquid water present in Gale Crater for maybe 1.5 billion years, which is a very long time, especially when you're thinking about whether or not these environments would have been habitable. And finally, the mineralogy and geochemistry suggests that there were many different environments which would have been habitable to ancient microbial life. And we didn't talk much about the evolution of the mineralogy, but in more recent samples, like at Old Soaker, we see many more salts in these rocks. So it's suggesting that these waters were drying up over time. And so maybe we're seeing evidence for the loss of liquid water on Mars around 3.5 billion years ago. Okay, I just want to end by showing you where we are today. We're down here at this feature, this ridge that we call Vera Rubin Ridge. And here's just a close-up of that ridge. And we're interested in this ridge especially because from orbital spectroscopy, we know that there's a lot of hematite here. So hematite is that oxidized iron mineral. So we know that there were, or we think that there were oxidizing fluids moving through here, or oxidizing waters. And here's just a few images of Vera Rubin Ridge as we climbed up it. I just want to point out that we see a lot of those thin layers of mudstone similar to what we saw below it. So it could have been deposited in a lake environment. This is a color image. It's a little bit stretched of the Vera Rubin Ridge, but I just want you to notice that there are a lot of different colors in here. Again, suggesting that the mineralogy and the chemistry of these different surfaces is probably very different. And so one thing we're trying to figure out is why are these surfaces so different in color, and are those color changes associated with changes in chemistry? Can those tell us about something about the ancient environment here? And so from the Vera Rubin Ridge, we're here at this star today. We're going to drive around down into what we call the clay unit. So from orbit, we know that there's a lot of clay minerals there. And then we're going to drive up into this sulfate-rich unit. So again, suggesting that these environments change from one where there was a lot of liquid water to, and not very salty liquid water, to one where there wasn't a lot of water and it was much saltier. So hopefully we investigate these environmental changes with curiosity. And just one final note, so we were talking about fans before. So this is another fan or delta here that everybody is very intrigued by. So again, so these rocks out here where we saw the fan are much, much older. So this is a much, much younger fan, and everybody's really excited to take a look at it. So, and that's what I have for you today. So thanks very much for listening. I'm going to turn it over to Paige to moderate, but I'm happy to take any questions that you have.
Absolutely. Well, first of all, thank you so much, Liz, for sharing these images of Mars and the surface. I'm telling you, my own cell phone or camera doesn't take what seems to be the great detailed pictures that they have. And observations and the observations you can make are just amazing. So first of all, thank you, Liz. And I hope the students out there have really gotten some basic understanding of Mars, curiosity, and these discoveries that continue to be made through observations of these images and data that have been taken. So at this point in time, it is approximately 10 minutes or 7 minutes to the top of the hour. And if you have questions, you can put them into the chat window. We'll pause at the top of the hour to sort of officially come to a close, and then Liz will stay on for a few extra minutes. So Liz, we've got our first question from Alpine Middle School, and they're in Texas. They're wondering, well, how long really have we been studying Mars? You kind of alluded to it in the beginning, but how long has it been?
Well, with telescopes, we've been studying Mars for hundreds of years, and that's actually how, maybe in the late 1800s, people thought that there was a civilization on Mars that had built canals because they thought they saw in these, pretty crude telescopes, they thought they saw these canals. But with NASA missions, we've been studying Mars for almost 70 years.
That's I guess you think back to
60 years, almost 60 years. Yeah.
In the 60s with the Mariner mission.
Yeah, exactly.
Yeah. So.
Yeah.
So from 1960 to almost 60, 70 years.
Yeah.
So and the learning still continues. There's always more data. As you saw, there was so many spacecraft exploring Mars, but there's so much more. The more we discover, the more questions we ask.
Exactly.
Yeah. So great question there, Alpine Middle School. We had another question from, let's see, this goes to Green Park Lutheran School. They're wondering if you can describe, and they're in Missouri, how are these rovers controlled?
It's a good question. So when we control the rover, it's not like with a joystick. You're not like go, collect, drive. We come up with a series of commands to instruct the rover over the course of 1, 2, 3, sometimes 4 days. And so we'll get together at the beginning of a planning day, the geology group that I'm on. We will look at the data that have come down over the last day, maybe over the weekend, look at the images and try to identify which rocks we might want to target to get geochemical data, maybe targets that we might want to drill, and also determine where we might want to drive. And so then we put together all of those commands to command all of the instruments to tell the rover where to drive, and then we send those up via the Deep Space Network here, and it goes to an orbiter around Mars, either Odyssey, Mars Reconnaissance Orbiter. Sometimes we use Maven, and that will relay the commands down to Curiosity.
Awesome. And there are people even here, other than Liz, we have many other scientists who have these jobs as are they called uplink leads and downlink leads, where they're part of the packaging of these commands that go out, and then of course you have to then get that data, retrieve that data so the scientists can look it over. So it is an interesting process, but yeah, I think some people think, is it a joystick that you're moving it around? But No, it's literally, it's very important commands.
Mm-hmm.
Awesome. Thank you, Liz. So here's a question from Duxbury Senior Center, and they're wondering, does the Curiosity's camera have the ability to resolve microbial life?
It's a good question. The MOLLE instrument is our highest resolution camera, and its resolution can go down to about 60 microns per pixel. And this is not good enough to look at microbial life, especially like ancient, simple microbial life. Certainly, if there were things like microbial mats that form like more macroscopic structures, we would be able to resolve those, but not like those individual microbes, which is exactly why we need to bring samples back, because we have all of this evidence for water on the surface of Mars. And it was on Mars around the same time that life was evolving on Earth. And so we think that Mars could have microbial life, but I don't think we're going to know until we return those samples and analyze them with the high-powered microscopes that we have here.
Well, thank you for the very thorough answer and for the great question, Duxbury Senior Center. Now, Murfreesboro, our group in Illinois, they ask a really interesting question because, you look at all of these names, and so they're asking, how do you or who names these places on Mars? Here, Reuben Ridge,
yeah,
and all of that.
It's such a good question. So we do have a naming committee on the team, and they've divided the path where Curiosity goes into different pieces, and each one of those pieces or quadrants is given a theme, and they're all geologic themes. So one quadrant, like where we were investigating the dunes, was the Namibia quadrant, because Namibia is very famous for their aeolian or wind-blown dunes. And so all of those names came from a place in Namibia, so like Namib Dune. Or there was a quad that was named after the Mojave Desert. And so that's where we got Pahrump. And we had a target called Mojave, so that's where those names came from.
And these are unofficial names, is that correct?
Yeah,
because
exactly.
Really the actual names of like Gale Crater or Olympus Mons, those have gone through a different system where these are official names, but these are unofficial, but it's nice that they're kind of theme related.
Yeah.
Very, very neat. Awesome. Now, just to sort of recognize the fact that we are at the top of the hour, I know many of you have to go on to your next classes or to lunch. And so for those of you that have to depart, thank you so much for joining us today. We're so glad to have had you on the line with us. And as soon as we can get an archive made, I will send it out to teachers. But for those that are staying on the line, Liz will stay maybe an extra 15 minutes or so to answer more questions, because I do see a lot of questions coming in. So let's go back to some questions. So back to the life thought. Smith Elementary, our group from Delaware, I believe, they're wondering if life did exist on Mars, what would it have looked like?
It's a really great question, and we're not exactly sure. We can guess what it would look like based on the most primitive life that we've found on Earth, because Mars, we think, was much more Earth-like 3 or 4 billion years ago. So we find similar minerals. We think that there were similar habitats. So we're guessing it would look a lot like it would on Earth. But it becomes an even more interesting question when you think about other worlds. So, some of the outer planets have these moons like Titan that are, they're not water worlds, but they are hydrocarbon worlds. And so there's liquid and solid, methane and ethane. So if life evolved in one of those worlds, what would that life look like? I don't know. I think that's a more...
And you're talking more microbial
Yes.
type life. Certainly not little people running
No.
across the surface.
No.
Microscopic microbial type life, which really would be interesting to be able to detect. But our current instruments don't have that detection ability. That's why it's so important to potentially bring back a sample.
Exactly.
Awesome. So here's a good question. I think a lot of people wonder this too. From Green Park Lutheran School, our group in Missouri, how fast does the rover travel?
Oh my gosh. I don't know its top speed, but it is not fast.
About turtle pace?
Yeah, I would say turtle pace. Maybe a little faster, maybe a fast turtle. I don't know. They can move pretty fast if they're hungry.
I guess they are. I guess turtles can move pretty fast, but really, in essence, it's pretty slow.
Yes.
That the rovers. And is there a reason why they do move and traverse the surface so slowly?
Well, you want to make sure that you're not, flying over things. I mean, these are very sensitive instruments that cannot be jostled a lot. You can't just jump over things. You have to be very careful even just driving over rocks, because our wheels are pretty sensitive, and they've gotten a lot of holes in them from driving over these pretty rugged terrains.
So safety is pretty paramount.
Yes, absolutely.
Excellent question there, Green Lutheran, and one that is a common one. They're not Speedy Gonzales, that's for sure. Now, Central Heights in Ohio is wondering how far Curiosity has traveled in the distance since 2012, and do you think they will ever find evidence of microbial life with this rover?
Excellent question. So we've driven, I checked, and it was 17.85 kilometers, which is a little over 11 miles in 5.5 years. So not super far considering how long we've been up there. But your other question was related to if we'll ever find evidence for microbial life with this rover. We will not, because we cannot. We do not have the instruments on Curiosity that can identify microbial life. We can identify habitable environments, and we can find the building blocks of life, so organic molecules, but we would have no ability to say whether those organic molecules were actually tied up in some sort of microbial organism.
And that's a great distinction, because habitable environments and finding evidence of that is different than finding evidence of microbes. So you need special instrumentation to do that, and you can certainly postulate, hypothesize, but the capabilities are only such that habitable environments are about it. So very interesting question from Central Heights. Now, Meadow Creek is wondering, and especially as we're getting into the holiday season, and Meadow Creek is from Texas, how long is one Mars sol? So they know that a sol is a day on Mars, and how many until Christmas?
Oh, great question. So a Martian day is just a little longer than an Earth day. So a sol is, I think, 24 hours and 36 minutes. And so how many sols until Christmas is the 7th, which is the 17 and a half?
So a little less than the actual number of days on here.
Yeah.
But very interesting question. I don't know if Santa Claus will visit Curiosity on Mars.
Yeah, I don't know either. I hope so. She's been very good this year.
She's been very good this year. So here's a question from Monmouth Middle School, and Monmouth is in Maine. And they're wondering, will Curiosity or any of the rovers, do they ever get brought back to Earth?
It's a good question. No. So none of these rovers have plans to come back from Earth, or come back to Earth. The Mars 2020 rover, which has not been named yet, it will launch in the year 2020, and it is going to collect samples in sample tubes and leave them on the surface for a future mission to go and pick up and bring back. So I guess part of that rover will come back. The sample tubes will come back from the sample. And that gives us an opportunity to actually look for microbial life.
And it's just way too expensive to bring these rovers back. And the technology to be able to do so as well is something that would require a whole lot. But monetarily wise, budgetary wise, it doesn't make any sense. So, and these rovers luckily have lasted so long to bring us back at least all the data and imagery, which is the greatest thing we could ask for. So here's a question from Corpus Christi Catholic School, not from Corpus Christi, Texas, but from Pennsylvania. And they're wondering what the largest hole is that Curiosity has been able to dig. Do they only drill, or can they dig as well? Can she dig as well?
So we can use, we have a little scoop to scoop up loose sand on the surface and deliver it to the instruments on the inside of the rover, sand and chemins. But that only goes down a few centimeters. We do have the ability to scuff, is what we call it, with our wheels. So sometimes we will drive a little bit into a sand patch to, look at the grains on the inside of a dune or below the surface. But the deepest that we can drill is only about 6 centimeters, so only a few inches down.
I see. But 6 centimeters can still reveal a whole lot about that subsurface.
Yeah, we saw that with the drill holes.
Absolutely. And that was really fascinating and really interesting, and so much that you can even think about just from looking at the drill hole finds.
Exactly.
Well, our school from Mexico, Aerospace Academy, is wondering about the energy and power for Curiosity, and how many years Curiosity will have power and energy to continue working on Mars.
Yeah, it's a great question. So all of the rovers and landers to date have used solar power. Curiosity is different. We use a nuclear battery. And that nuclear battery, I don't know its exact lifetime, but I think it's supposed to, basically supply us for at least 14 years. So, another 8 or 9 years of good battery lifetime.
And, what was the mission success for Curiosity? Was it 2 Earth years was considered mission success? And we've been on the surface for how long?
5.5.
So NASA does try to be conservative and set realistic goals, but 14 years or so, we've been on for 5.5 years. Let's hope we keep going for another 14 years or more. Thank you for the question, Aerospace Academy from Mexico. Now here is a question from Monmouth Middle School, and they're wondering, and they're related. Now, Monmouth is asking, when do we think we'll have a person on Mars? But Alpine Middle School asked something somewhat related to these extreme temperatures. How will we be able to put people on Mars?
Yeah, so the thought is that people will be on Mars, at least from NASA, in the 2030s, so 20 years-ish. But of course, that could all change with commercial space flight. So, people like Elon Musk and SpaceX are talking about putting people on Mars much, much sooner than that, and even colonizing the surface of Mars. So we'll just have to see how that commercial space flight plays out. But I'm hoping within the next 20 years we see people on Mars. And so then the related question about, how with these super cold temperatures and this radiation coming from space, how on Earth can we put people on Mars? So, and it will require a lot of shielding. So the habitat will have to be shielded, and we'll have to have, a special atmosphere on the inside. The spacesuits will also have to be shielded, and they bring their own atmosphere with them so that they can breathe. but people talk about terraforming Mars or turning it into a much more Earth-like place, and with the lack of the magnetic field, that is impossible. You will always have to have some sort of habitat or bubble to live in.
And if NASA were to send people to Mars, there would certainly be the expectation that the intent would be to bring those people home.
Absolutely.
As well.
Yes.
Yeah, and all those safety precautions would be put in place and testing to ensure that that could happen. So
Yep. Safety is number one.
Unlike robotic spacecraft, which we do leave on the surface, with humans it's a totally different ball game, which takes time for tests and to make sure there's enough preparation to do it all right and do it safely.
Absolutely.
Now, related to this, Alpine Middle School, with this whole extreme temperature thing, they're wondering, so how does the equipment on these rovers not freeze?
Yeah, and it's from that nuclear battery. So we do have a lot of power and heat that's generated from the decay of nuclear material from radiation. And so we use that heat to warm our instruments. And, it's wintertime at Gale Crater, so we actually spend a lot of our time just waiting for instruments to heat up or waiting for the arm to heat up before we could move it. And, even a couple of weeks ago, we had a small fault where we wanted to move the arm, but we didn't spend enough time heating, so the arm didn't move. And so we got an error that came back the next day that said, it was too cold, can't move the arm, try
again later.
Heat up a little longer.
Well, I'm sure that wasn't a fun message to receive back.
Those errors are never fun to receive.
Right. But what's interesting is the scientists and engineers have to figure out when they get these faults back, these error messages, what do they do in order to make that not happen again? Exactly. Awesome. So here is a question from Green Park Lutheran School, and they're in Missouri again, and they were wondering if the gray powder could be a dried out aquifer. Is that at all a possibility?
Yeah, absolutely. So, we saw this evidence for groundwater moving through these sediments. So we know that there was active groundwater. We're not sure if we could truly call it an aquifer, and how long-lived that groundwater would have been. But yes, subsurface water was definitely present in Gale Crater.
And the whole idea of where did all this water go from 4 billion years ago to now, some of it really is locked up into the surface, and that's where you see it in all the minerals. Is that correct? Yeah,
absolutely. Yeah, so a lot of the water was lost to space. Some of it is locked up as water ice in the poles or in the near subsurface, in the near surface near the poles, but also in these hydrated minerals.
Very good evidence that supports what the scientists are finding. Excellent. So here's a question from Monmouth Middle School, and Monmouth is again from Maine, and they're wondering, are there other countries with rovers on Mars?
No, there are not. There are European orbiters. We do have international partners on Curiosity. So some of the instruments are provided by other countries, and that'll be the same for the 2020 rover. And I'm trying to think if there are any rovers planned to Mars from other countries right now, and I can't think of any. There are certainly orbiters going up, from India, from, I think, the United Arab Emirates is going to send one in the next few years. I do know that a lot of other countries are really focusing on the moon, sending robots to the moon, but also sending people to the moon.
Interesting. It should be a very interesting decade for exploration.
Yeah.
It sure will. So here's a really important question, and I think one that probably has multiple answers. And this comes from Meadow Creek in Texas. and they are wondering if you want to go to Mars, or you even want to study Mars, but if you want to be an astronaut and go to Mars, what should you study in college?
It's a really good question. You definitely want to have a good STEM background, so science, technology, engineering, math. I'm trying to think, but in any of those fields, you can actually become an astronaut, or you can study planetary geology. So my path was through geology, but there are many engineers that work with us on the rover. There are biologists, there are chemists, there are physicists, and so there really are a wide variety of career paths that you can take. I would definitely make sure you just have a good base in math and physics, probably a little chemistry. That's just what I think.
And having probably a diverse background and one in which you have multiple skills. I think about our current astronaut class that was selected, our astronaut candidates, and they range from medical doctors to flight engineers to geologists to
there's a biologist.
So that diversity and being able to show that that you haven't been afraid to get involved in a lot of different things.
Yeah.
So get involved in school things, whether it's sports or clubs or science-related clubs. The more involved you are, that gives you a lot of diverse experience in things. But I agree, sciences and math, and even web designers. A web designer isn't going to go to Mars, but a web designer is certainly going to help share that story, which is really, really neat. So that's a great question. And I would probably also say, and I don't know if you'll agree, follow your passion.
Yes. Yeah, because if you don't like what you do, you're not going to want to do it.
That's right. And I don't know if you can tell. I think Liz likes what she does. And that's where, being so busy doesn't feel like you're busy, because when you love what you do, you just want to do more of it.
I know. I'm happy to come to work.
Which is a great thing, which is a really great thing. And so for all of you out there, follow your passion and you'll never work a day in your life. Let's see if there's any other. It looks like Murfreesboro Middle School has a question, and it's an interesting one because they're wondering if there is a centralized agency that decides what countries can send things to places like Mars, or is there a coordination, or how does that work?
That's a really great question, and as far as I know, no, not yet, but we might be approaching something like that, especially with the moon. So you think about, when countries are sending a lot of people up to the moon, are they going to be competing for resources? How are we going to, assign who gets which part of the moon, if it comes to that? But in terms of sending things to Mars, there is no, broader committee that assigns who gets to go. It's really, which countries are interested in the scientific research and which countries are willing to fund that scientific research. So, your taxes are going towards things like Curiosity and Mars 2020.
And it's not much either. It's probably a penny on the dollar that people pay in taxes to support NASA exploration. So people might think that, my gosh, how much money is all of this costing? But really, it's pennies on the dollar from our taxpayers. And the work that we do here is on behalf of our countries, and same thing with other nations. But it is great, the collaboration amongst the science world. People from different countries. There are conferences where all these people come together, and we can learn from everyone, from ourselves, as well as the things that are being done on other countries as well. So that collaboration is so important.
Absolutely.
Yeah. So or international missions. You think about the International Space Station and the diversity of folks that have been up there to the ISS. It really is a community and an earthly effort from all around the world. Now, I think I have one other question from one of our NASA Solar System ambassadors who is wondering between Martian meteorites and specific terrains on Mars, has there been any connections to specifics between some of these shergottites or meteorites that we have found and their origin, their original location, where they may have come from?
Yeah, it's a good question, and I am not as up on the meteorite literature as I should be, but from what I can tell, I mean, I think you can hypothesize about from where things could come from based on surface compositions. But the other thing about meteorites is that they come from much deeper in the surface than what we can see with orbiting spectrometers. So it makes it much more difficult to say where these meteorites might have come from. We do use some of the data from Mars meteorites in our interpretations of the Chemin data, so we use a lot of the mineral structures and chemistries from that have been analyzed from Martian meteorites, assuming that those same minerals and chemistries might be present in the samples that we are looking at from Gale Crater with Chemin.
And it's interesting because meteorites are so fascinating, and Liz mentioned it is one of the ways scientists study the geology on other worlds, but in some cases we don't even know the origin, the planetary origin, or the parent body of those meteorites, let alone a specific location. So that's, I think, another reason why it's so important to get samples from Mars that we can choose, pick up, know where they came from to help us better understand a little bit more of that context. Yeah. So meteorites, as great as they are, there's so many mysteries and unknowns to them, but it's all part of that puzzle.
Yep.
So sometime in the future, we here at the Astromaterials, we house the meteorites collected in Antarctica. So one of these days, perhaps in 2018, maybe we'll do a virtual tour of our meteorite lab, so you can see where we house our meteorites right here in this very building we're sitting in. So great question, and for all of the groups out there, really great questions. I hope that you took away how much we've learned and all of the discoveries made by Curiosity through what Liz has shared with you, but also that you'll take away how much more discovery has yet to be made from Curiosity and other robotic missions to Mars and throughout our solar system. So with that, it's about 25 minutes or so past the hour. So first of all, Liz, thank you so much for sharing.
Thanks for having me.
Thanks for your time and your extra time. Any last comments to the groups that are still on the line there?
Well, thanks so much for listening and for your great questions. I can tell that, you are very science-minded. So I really appreciate it, and I hope I get to show you more about what Curiosity has discovered later.
That sounds awesome. So with that, we'll bring things officially to a close. Thank you, everyone, for joining us. And until next time, have a great and safe holiday season. And we look forward to connecting with you in 2018. So with that, thanks, everyone.
Thanks, everybody.
Have a great day.
Bye-bye.